Hi, during this week, we're going to be studying rate applications, which are word problems with 3 or more variables, and what's something called local linearization and what differentials are. So first of all, with rate applications are word problems sound kind of scary, but remember with these kinds of word problems, make sure to draw a picture, organize the information, write out the question and the information using calculus notation, like variables like x, or derivatives like dx dt. Remember also that formulas aren't always going to be remembered. They're things that have been learned in your geometry class or your pre-calculus class. And honestly, you may not remember all the formulas. Do you remember the volume of a sphere, the surface area of a cylinder, the formula for calculating interest at 7% every month? Those kinds of things. Don't feel shy about looking them up or Googling them or emailing me to ask me what those formulas look like. But once you get a formula, the derivatives are just like we've done before using the chain rule. Make sure you use the correct like dx dt notation, dy dt notation. These kinds of problems don't work with that prime, the f prime x type notation. By the way, the reason why they have dx dt in my little example here about a wall and there's a little ladder along the wall and it's kind of sliding away from the bottom of the ladder wall combination thing is because it's sliding in time. We have a distance along the ground, which is x. We have a distance along the wall, which is y. We have the ladder length, which is z. But all these things could be changing on time, which is why we have so many different variables. So that's kind of the big idea in 3.9. In 3.10, we're doing something called local linearization, which honestly is way easier than they make it appear in the textbook. They're going to be using a lot of fancy notation and a lot of words, but local linearization is literally just finding the equation of the tangent line and using that tangent line to approximate the value of the function. So here my little picture over here on the left-hand side, I have a function fx in black. I chose a random point right here, and we can draw a tangent line at that particular point. Tangent lines have the equation y equals mx plus b. They're going to use lx equals mx plus b, but it's the same thing as y equals mx plus b. And then you might be able to see from my picture here that if I choose any value x, as long as it's very close to a, as long as x is near a, then the y height of the y height of the tangent line and the y height of the function, if I can draw a straight line, are virtually the same. They're off by a little bit, but the error is very small. So we're going to be using a tangent line value to approximate the y value of a function for x values that are close to some specified a. They'll tell you what a is, and then you're going to approximate a value close to that a. And lastly, you're going to learn about differentials. So my last example down here is I had a simple y equals x cubed equation. We've differentiated those kinds of things before, and you get dy dx equals 3x squared. The new idea presented here on differentials is we're going to think of dy and dx as separate things. So I could, for example, move the dx to the right-hand side just by multiplying both sides by dx. And dy and dx are called differentials. So those things are going to be considered an own entity. And to help you think about that, think of dy as sort of the change in y, like delta y. So you can think of this as the change in y is 3x squared times the change in x. There's a little prelude for our work for this week. Make sure to reach out via email or drop in by my tutoring hours if you have any questions or need help with anything. All right, good luck.